and welcome. And appreciate you inviting me this morning. And this morning, my time, I'm in Colorado in the US. I know it's all over the world for many of you, so I appreciate you staying up late in Japan. And I hope this is a timely topic. Um, I just finished the Space Symposium here in Colorado Springs this week. There's about, 8,000 people came from all over the world. And almost every one of my colleagues I talked with, at some point in the conversation, AI came up. So AI is on the tongue of pretty much everybody in the world, certainly engineers. And I've been thinking about it for a long time. And most recently put together this presentation because I think it's very important that we understand where does system engineering fit in this AI world. And I think we're all trying to figure out where AI fits in our daily lives. And certainly there are people worried about AI taking over their jobs. Um, so I put together these thoughts, and that's just that what they are. There's some thoughts on where I think AI comes in, and actually the key theme here is where does system engineering fit in all of this? I'm going to warn you, I've had some internet problems this morning, so if I have an emergency, I'll have to switch over to my phone. But so far, my internet seems to be behaving. Um, Please put any questions you have in the chat, and Fatima said she would holler out to me if there's a question, or feel free to stop me as we go. But we'll have some time for questions and answers here at the end. Fatima did a good job of introducing me, so I don't need to repeat who I am there. That's my bio. I'm with a small company called Teaching Science and Technology. We do training and education all over the world. So we've done training at Melco, JAXA, and NASA, European Space Agency, and we kind of help organizations onboard new hire folks in system engineering and help with folks that are going on from technical disciplines into system engineering, and even help organizations start up new projects and things like that. So we work at a variety of different training programs, from foundational to tools and techniques to applications. And we have a whole wide variety of training that we do. But two things I'll point out, because recently we just added to the UNISEC website, we have two on-demand courses you may be interested in, and we have a discount for UNISEC members. So one is Understanding Space, which is an introductory course, and one is a bit more advanced Designing Space Missions and Systems course. So I wanted to make you aware of those. We just recently added those in partnership with UNISEC. So you might want to let your organizations know about that opportunity. So where are we? It's hard to believe. So for me, my introduction to AI came about not quite 2 years ago. I guess 2 years ago, my son was I think he was just first year at university, and said, "Hey, Dad, have you heard about this thing called Chat GPT?" And I'm like, "Oh, what's that?" So my son introduced me to it, actually, and we spent part of our Christmas vacation exploring what Chat could do for us. And I've been an avid user ever since. And as we can probably see, and I imagine most of you can agree, a lot of us are using AI tools every day. I've been using them almost every day to do things, even keep track of my day-to-day agenda, but also doing things like generating concepts, helping with trade studies. I found it very helpful supporting proposal development and document development, exploring alternatives. And what we're seeing is this has kind of helped increase the pace of engineering work. And what AI, kind of the theme I'm going to talk about here, is that AI can really help us look at more options quickly. That can be good or bad, as we'll see. But the fundamentals don't change, right? We live in what I like to call the system engineering universe. This system engineering universe has 4 dimensions: cost, schedule, performance, and risk. And everything we do, every decision we make in every project we're in, we have to balance those 4 things. And AI can maybe help us with that, but it's not going to do that, right? And that's where we're going to kind of explore in this discussion today. A lot of the discussion around AI now, is kind of concerns about how will AI help us design systems? Will it replace engineers? Will it automate system engineering? But I think we're kind of missing the point here. The AI is really accelerating the creation of what I'm going to call engineering artifacts. But at least so far, AI does not assume responsibility for the decisions we have to make. So we're still going to succeed or fail based on what we decide to do and what we commit our projects to do. And that's where we need to understand how AI then can fit in to support that. If we think about any project, and space is no different, the road to space, the road to any project is paved with a whole bunch of decisions. We have feasibility decisions, architecture decisions, evidence decisions, and they're all those decisions have to balance cost, schedule, performance, and risk. And that how we manage that is really what, as we'll see, system engineering is all about. And I think we can argue that projects as an enterprise, we don't exist to create paper. We don't exist to create reports. We don't exist to create requirements documents. We exist to create informed decisions, decisions that commit time, resources, with the promise to our stakeholders that we're going to deliver a capability on time, in budget, that meets their expectations with acceptable risk. Now, requirements, architectures, models, we need those things, but they are not ends in themselves. They are the means, they are tools that help them. And they need to be developed in a way that supports understanding, alignment, and decision making. And so we want to measure our progress in our system engineering, not by the volume of things that we produce, but really by the quality and how it affects the maturity of our thinking. And so that's where we're kind of trying to put in and see where how AI can accelerate that, but doesn't necessarily replace that. So if we look at how decisions get made, we think of this funnel basically when we start on the left with high uncertainty, and over time we make a lot of decisions. And those decisions are sometimes very big decisions. How are we going to go to the moon? Okay, we're going to do, I think a classic example I use in class a lot is on Apollo. Is like we chose on Apollo, the Apollo program in the 60s, to do lunar orbit rendezvous in lunar orbit. That was a decision. There were other ways to do it, but that was the way it was chosen. And that architecture drove everything else. That's why the lunar module looks the way it does, because of that architecture decision. So we make these decisions that commit us to certain design choices. So we have to define, but to do that as a team, we need to understand our objectives, understand our constraints, understand what we're trying to do with performance, and be aligned with our stakeholders, like making sure the decisions we make are what the stakeholders can live with. And then when we do that, we will be committing to specific courses of action. And usually that's often no going back. I mean, once we make these decisions, it's pretty hard to go back on those things. And so we want to be clear about where those decisions get made and making sure we make those decisions with the right information. So we developed this thing we call our project decision domains, as I kind of alluded to earlier. So these domains focus on things like feasibility and context. Okay, what can the project, is the solution I'm proposing even feasible? Do I understand the context of the mission that it's going to be deployed in? What are the architectures and what are the options within those architectures? As I mentioned, Apollo. Okay, should we, at one point we were talking about building one really big rocket, lifting off from Earth and landing that same big rocket on the moon, right? That's a different architecture than what we ended up with. And so different trades drive us in different directions. How much execution and rigor decisions have to do with how much rigor we put. Dr. Sakamoto introduced the CANSAT. CANSAT. Okay, sorry about that. Yeah, I was worried about my internet.
No worries. Yeah, thank you.
Okay, so and then we have, I'm not sure where I cut off, but we have architecture decisions, execution and rigor decisions. As I said, you're not going to use the same amount of rigor on a CANSAT that we do on Artemis. What evidence do we need to collect? How much verification, validation goes into the project? What's our operational environment? Well, how are we going to sustain the system? And then how are we going to collect and organize information? about our system. We're going to do it in documents, we're going to do it in models. These are all decisions that we have to make in engineering, and those decisions are driven by what I'm going to call artifacts. Um, those artifacts get developed as part of system engineering. So Dr. Sakamoto showed the classic system engineering V, and I'm showing our version of the system engineering V there, where we start with a need and we turn that into a capability. On the left side, we do design. On the right side, we do our design and build and test. And in the middle are all the things that we get to manage. That's a classic way of looking at it. The way I've been teaching it, though, lately is thinking about it more as a circle, because the V is nice to talk about as you're teaching it, but when you're actually doing it, it turns out things are way more iterative. And so we think about it more as a set of tasks that have to get done. And those tasks can be done in a variety of order, depending on the project that you're doing. But the key part of these tasks is developing artifacts, as we said, things that are evidence of our decisions, evidence of the things that we're developing. So our goals and objectives, our requirements, our architecture. I'm going to, okay, hopefully that's good. So our architectures and all those things that are important to supporting the decisions. And so we can see this relationship then between the decision domains and system engineering, right? So system engineering is creating the artifacts, the decision domains are using those artifacts to help make decisions that drive everything we do across the life cycle. So that's the framing I want to provide here as we think about AI now. So where does AI enter here? So teams are starting to use AI for concept development, trade studies, proposal development, product development, even sustainment. Um, and currently, at least in the near term, it's mainly I see AI helping us in that what I'll call our artifact generation and analysis loop. And we can increase the speed, the breadth, and the iteration rate, but we still have to make the decisions, as we'll see. So, because what AI is not doing is assuming responsibility for the program outcome. So, if you're the project manager or system engineer, you're still gonna, your success or failure still depends on how well we deliver capability to our users. AI, we're not gonna be able to blame AI if that doesn't work out. So, the AI can help us produce possibilities, but it's still up to us humans to define the parameters and make the decisions. So where I really see the impact is in early phases. And so we can help us early on, how AI can help us early on in proposal development, requirements development. In fact, we did a project last year with one of my graduate students using AI to develop requirements. And we actually used AI to check AI requirements. So we can help with that. We can do mission concept exploration, architecture definitions. And you can kind of see in my graphic there, kind of showing my little, agile loops, that we can do more, potentially do more iterations in the same amount of time. So that can help us do faster concept iterations, explore different and more alternatives, and maybe shorten time for analysis. Um, but that does not come for free. We still have to align our what we're doing with the project and have a disciplined decision. So that means potentially we have an explosion, I should say, of options. So with these AI tools, we can explore more options. We can do more trade studies. We can iterate faster. So now the bottleneck is not generating options. It's really the bottleneck is in making decisions because more options really increase the importance of us being able to make structured decisions and being ready to commit to those as we go. So how does that affect you if you're the chief engineer? If you're the engineer on a project, and you're using AI and your teams are using AI, then your responsibilities shift a little bit. Your responsibilities now are more focused on how do I frame the decision space? What does the trade space look like? Defining up front what are the constraints and assumptions. So I'm sure many of you have been using AI, and the more specific you are about defining the problem,
the better the result. If you know the so if you can get as you, if you can get very, very specific about what you want, you're more likely to get what you want. And I'd say a key thing, and I put it in italics there, is validating what AI puts out. So if you're like me and you've used AI a lot, sometimes what it comes up with is just wrong. And you even math sometimes is wrong. And you have to be able to look at it and say, that doesn't look right. There's something going on here. Um, and often, it'll say, "Oh yeah, you're right. I did." The AI will correct itself once you point out the error. And and I ran across this metaphor here recently from a colleague of mine, actually this week as we were talking. And I put a picture down there that many of you will have no idea what you're looking at. But that picture at the bottom right is what we used to call a slide rule. And there may be a few of us in the audience that remember using slide rules. Um, and the slide rule was a very useful way to do calculations before we had calculators and computers. The thing about a slide rule, though, is that to use it effectively, you had to already know the answer within an order of magnitude. Because the slide rule could give you an answer, and it was either 2 or 20 or 200,000, and you needed to know which one it was. And I think that's an interesting metaphor as we think about using AI. We have to know what kind of answer we're looking for, at least within an order of magnitude, so that when it comes out, you say, yeah, that looks about right, or no, that doesn't look right. And so that it doesn't relieve us of the need to understand approximately what we're looking for. So the chief engineer's role then is about integrating that human expertise so that we can leverage the AI-enabled analysis to support those going back to those decisions that we were talking about. So what does that mean for the program managers? Well, the program manager still has ultimate responsibility for all the decisions. Again, the program manager cannot blame AI for the bad decision. They can blame it for, bad data, but that's kind of a cop out. But it's really up to the program manager to make the decision. Those decisions create commitments for the team and the project and need to be aligned with the stakeholders. And of course, it creates risk. No matter every decision we make comes with some risks attached. And so while we can accelerate that technical analysis, it doesn't replace the program accountability that the project manager has to assume. So we still have to, as project managers, be aligned with the stakeholders around the decisions we make, understand what the implications are for risks, ensure that everyone understands those decisions and take ownership of those decisions. Again, it's not the AI's decision. They don't own that decision. They provide their calculator giving me a number. I have to decide what to do with that number and then balance it against other aspects of the project, such as cost and schedule and things like that. So again, we accelerate the analysis, but it doesn't assume accountability for what happens next. So the risks we run as we start bringing AI in, and I'm not saying not to, I think we should embrace AI, honestly, but we need to be aware of what we're getting ourselves into. So we can accelerate some of the engineering work, but we need to be careful about shallow or incomplete trade studies. Often AI can give us the illusion that we're looking at something pretty deeply, but in fact, we're not. And we can gain kind of false confidence in outputs that look plausible, but maybe really aren't. And we have to be clear about how that data that comes out can affect the architectures that we've committed to. And is that going to cause differences, especially across different teams, in how they commit to those architectures? We have the danger potentially of changing our requirements, and so as we go along, and often we lose track of ownership. So we have multiple teams using multiple AI models. Who really owns this data, right? Where's it coming from? We call the single source of truth for that. So just because the outcome from the AI tool is plausible doesn't mean it's been validated, right? We still need to potentially independently check those numbers. And that speed of churning out things can actually mask some misunderstandings of what's happening underneath. Because again, if you're not clear about the assumptions and constraints that you put to the AI, it could be making a different set of assumptions that lead you down a different path. And so we want to be very clear about that. So guidance we'd suggest for teams is, again, I see AI as a powerful collaborator. I kind of think of it as my sometimes my collaborator, sometimes my graduate student to help me with things. It can help generate options. It can help go down and look at trade spaces very quickly. You can draft, very nice for drafting artifacts and documents and reviewing documents. But going back to what the team needs to do and kind of shifting responsibilities here is be kind of go back to the basics. I mean, when I advise a lot of projects around the world, and one of the things I see very happens a lot, this is even, way before AI, is that teams would be, I would say down, we call it down in the weeds. They'd be down looking at very detailed requirements for the system before they'd really even defined what they wanted the system to do. And so I think this is a call for all of us to go back to basics and say, hey, before we start bringing in these tools to do, what seem like very amazing things, we need to establish our ground rules. We need to establish what our expectations. So what are the constraints? What is the intent we're trying to do? I'm actually working with advising a team right now, and they're building a project for a customer, and we're down looking at requirements. But next meeting we're going to have is going to be going back and looking at the basics of, okay, well, we got these requirements, but are we clear about what we're trying to do? And look at our decisions that come out, or sorry, look at our data that comes out of AI, and rigorously validate that against maybe other independent evaluations. Keeping track of our architecture and making sure that that data doesn't cause that to drift. Document those decisions as they come out, and try to not to converge too quickly on decisions before we fully vetted them. So again, we can accelerate the preparation for decisions, but not the speed of the decisions themselves. And so that kind of shifts our way of thinking a bit, I would say, within projects. What does that mean for our workforce? A lot of the conversations I had this week at the Space Symposium are around what do we tell new engineers? What do we tell students of engineering right now? And even engineering schools, those of you that teach at universities, I'm sure are all already grappling with those decisions of how much to allow students to use AI. I mean, I grew up where we did, my graduate studies, we did homework set after homework set, right? We ground through and solved problems on paper and had to, solve, Kepler's equation and, do interplanetary transfers on paper. Is that necessary now? Do we still make students do that? Or AI can do it faster, so is there something else we should be doing? And that's a whole philosophical discussion about education that we're going to have to be having. What I would say, though, is it shifts what we really want students and engineers in general to be able to do. It's not, yeah, they need, I think, personally, I think they still need to be able to grind through the rocket equation so they understand how it's used. But more importantly, or just as importantly, they need to be able to frame the problem for the rocket equation up correctly. What is the delta V requirements? What is the specific impulse we're going to assume? And then understand how to evaluate those options and look at the trades. And being able to validate the requirements, which might mean go over here with good old pencil and paper and double check the numbers to say, yeah, that looks about right. And then be able to integrate those decisions across the domains and be able to defend them. And I think we're going to start seeing a world where people say, well, the AI said, and that I don't think that's, just because the AI said it doesn't make it true. We have to be able to somehow independently verify that. And so that brings our skill sets, I think, back to a more basic level of being able to make sound, well-informed technical decisions based on the data that we're given. So what changes and what doesn't change? I think we're all seeing how AI is changing the pace of work. It's generating more options for the teams, but it's not changing the responsibility. And programs are still going to succeed or fail based on the clarity of the intent, how well we define the problem, the quality of the decisions we make based on the data that we have, how well we can get everyone aligned around those decisions, and still taking ownership of the commitments that we make. My bottom line here is that in an AI accelerated world, system engineering, I would say, matters more, not less, because we are still responsible for the decisions and the consequences of those decisions. Humans still own that. And so we need to see how we're going to kind of step up, I would say, our system engineering game and be ready to use AI most effectively. So thank you for your time and attention. We have time, hopefully plenty of time. I apologize for the little technical issue I had there with my internet. Hopefully I'm coming through okay. But we have plenty of time, I think, for some questions and discussion.